Hello students, so today we'll discuss about sense amplifier based registers. So in earlier videos we have seen about registers that were realized using master slave concept and also pulse registers that used glitch technique. So in this sense amplifier based register, the technique utilized is the utilization of sense amplifiers to realize the same edge triggers registers. So, the sense amplifier circuits accept small input signals and amplify these input signals to generate rail to rail swings. That is, you can either get the output as 0 or you can get the output as 1 or high. Sense amplifier circuits are extensively used in memory cores where the difference between the input signal is said to be a very small signal. So, this diagram shows the sense amplifier based register. Primarily it can be divided into two parts, right? So one part you can see is nothing but the part which is highlighted in blue is nothing but a NAND cross coupled SR flip flop, which you would have studied very well in digital circuits, right? So it's fundamentally an SR flip flop using two cross coupled NAND gates, right? So depending upon the values of inputs that you receive here and here, your output of flip flop will be set or reset, right? Secondarily, you have this part which is highlighted in red, which is called as front end amplifier. The primary function of this front end amplifier is it generates output at node L1 and L2. You can see that the value at L1 only is fed to this NAND gate, the value at L2 is only fed to this NAND gate. So the voltage at L1 and L2 is based upon the inputs applied here. So the differential inputs are in and in bar. So why it is called as differential inputs? In and in bar are complement of each other, and that's why it is called as differential signals, right? So the difference between these signals is only amplified and available at L1 and L2 based upon the value of this clock, right? So this front end amplifier, initially it will be pre-charged. The meaning is that initially when the clock is low, when we see in the detailed circuit operation, we will observe that L1 and L2 value both will be pre-charged to VDD when clock is low. When clock is going to be equal to high, depending upon the value of the differential inputs in and in bar, you will be getting the value of L1 and L2, which is then passed down to this SR flip flop, and it produces a output as out. So you can see that initially front end amplifier is pre-charged, and then when clock is high, it samples a differential signal on the rising edge of the clock. This SR flip flop outputs of the front end amplifier, right? So that is nothing but L1 and N2 are given to the inputs of the NAND flip flop that holds the data. And it also ensures, this flip flop also ensures that differential outputs switch only once per clock cycle. That is, for one clock cycle you can ensure that one data is being latched to the output out. So this slide is just to give you an insight about how NAND based SR flip flop. So you can see that this is a NAND input NAND gate based SR flip flop which accepts input S and R, and you can see that what are the conditions in which it will operate. So you would have already studied that. So when both set and reset are is equal to 1, the previous value of the flip flop will be maintained and hence no change, whereas when set is 0 and reset is 1, in that case you will be getting your Q equal to 1 or your flip flop will be set. Similarly, when set equal to 1 and reset is equal to 0, your flip flop will be reset, meaning Q equal to 0, right? And then when you are getting set equal to 0 and reset equal to 0, it is nothing but an invalid state, right? So this is just to give you an idea about how this SR flip flop. So let us discuss this operation of the circuit. So here L1 and L2 are nothing but outputs of the cross coupled inverter, or you can tell it is output of the sense amplifier. M1 is called as evaluation transistor. Why it is called as evaluation transistor? We have already seen in dynamic circuits, when clock equal to 1, right, this circuit will M1 will turn on and the circuit will evaluate based on in and in bar. right? Whereas during pre-charge phase, when clock equal to 0, this M1, which is evaluation transistor, will be in off. So since this is in off state, this value of in or in bar will never propagate to the output of sense amplifier. And M4 is called as a shorting transistor, whose significance we will see at the end. So let us first see the pre-charge phase. So when clock is equal to low, M1 will be said to be in off state, thereby disconnecting in and in bar from L1 and L2. At the same time, when clock is 0, M1 is in on state and M10 is also in on state. Hence, we can see that this L1 is pulled to VDD. Node L1 is pulled to VDD. Node L2 is also pulled to VDD. It is not pulled to ground because M1 is said to be in off state. Hence, we can tell that when clock is 0, L1 and L2 is pre-charged to VDD. Right? So, here this NAND gate input is 1 and here this again NAND gate input is 1. We have already seen for the SR flip-flop, when the inputs S and R is equal to 1 1, this flip-flop will be holding its previous state, right? So whatever will be the previous state will be held. So NAND SR flip-flop holds previous state, right? In this condition, when clock equal to 0, we can ensure that the differential signals in and in bar don't affect the output during the low phase of clock, right? Next we go for clock equal to high. So when clock equal to high, M1 turns into on state, which is called as evaluation. Why it's when M1 turns into on state, definitely the impact of this in and in bar will be included in the circuit, right? So based on the differential signals in and in bar, it depends upon which is going to be 1 and which is going to be equal to 0. So M2 and M3 will be enabled so that the difference between these two signals is amplified and obtained at L1 and L2, right? So for example, it will settle into one stable state. Either L1 will be 1 and L2 will be 0, or L2 will be 1 and L1 will be 0. So it will settle on to any one stable state. So let us analyze for this one case. So for example, we are taking as in equal to high, right? We know that during evaluation clock is high, so M1 is on. At this case, I am taking in as high and in bar as low. So when in is high, M2 is in on state and then M3 is in off state. So when M2 is in on state, automatically L3 will be pulled to 0 and L4 will be holding the previous value, which is nothing but 1. So so here L3 is 0, right? And at the same time L3 is 0 and L4 is equal to 1. At the same time, you can see that the previous values of L1 and L2 was equal to VDD, right? So this VDD will make M7 into on state, M7 into off state, and the same time it will also make this M8 into off state, right? And we can see that the same thing is also applied to M5, and again 1 is also applied to M6. So the previous values of L1 equal to L2 equal to VDD will turn on M5 and M6, right? So already M2 was on and it was having the value of 0. So now when M5 is also on, it is pulled to the value of 0. At the same time here, M3 was said to be off and M6 here is said to be on state. So L2 will be holding the previous value of its value, which is charged to VDD. Hence we can see that in the case when in equal to high and in bar equal to 0, we will be getting the value of L1 is equal to low and L2 equal to high, right? So L1 is equal to low and L2 is equal to high. So one input here is low and the other input here is high. So reset is 1 and set is 0. So automatically the output of this flip-flop will be equal to 1, which is based on the previous value of previous SR flip-flop circuitry that we have seen. So this is the operation of this sense amplifier, which you can verify it again for in equal to 0 and in bar equal to 1. In that case also you will be getting the output value as 0. So we can see that difference between these two so here we will see what is the necessity of the shorting transistor M4. So the need of the shorting transistor M4 is, if you have this shorting transistor, the voltages at nodes L1 and L2 or the outputs of the sense amplifier will not be disturbed even when there is a change in input during the evaluation phase. Previously itself, we have discussed that during evaluation, the inputs are allowed to change only once. But in case during evaluation, the input changes multiple number of times. That time also, we should ensure that the circuit is undisturbed and the previous values are maintained. So this is attained by means of this shorting transistor. So here let us look into a condition where in is 1 and in bar is 0 during the evaluation phase where clock is high. But however, we are seeing that the input is changing for the second time for 1 to 0 and from 0 to 1. So in actual working, what we expect is, even though the inputs change, we expect the volt outputs of the sense amplifier L1 to be 0 and L2 to be equal to 1, which should be in an undisturbed state. Right. So to analyze this, we are taking two conditions. One is the operation of the sense amplifier without the shorting transistor and the operation of the sense amplifier with the shorting transistor. So without the shorting transistor, you can see that when in changes from 1 to 0, right, this goes into this transistor goes into off state and the node at L3 is said to be floating, right. You will be having a leakage path which occurs because of previous values of L1 and L2. So because of this leakage path, this L3 node will be connected to VDD, which is nothing but 1, that is VDD, and it is also said to be floating. We do not want this change to occur because it changes from 0 to 1. Obviously it changes this value at L1 also from 0 to 1, which we do not acquire to occur, right. So this happens because this node is floating and it is in a high impedance state, right. That is why the node holds a value of 1. So what we do is we put a shorting transistor. When you put a shorting transistor over here, and this shorting transistor is always said to be in on state by connecting the gate input to high. So what happens here is, this node, even though the input changes from 1 to 0 and even though you have a leakage path over here, since this is going to be in on state, this node here is not said to be floating. Instead, when in bar also changes from 0 to 1, this will also be in on state. So this node is not floating and it is connected to ground. In this case, your 0 does not change to 1, whereas this voltage at node L3 is still maintained as 0, right. So this is the reason. So this is maintained at 0 just because of this shorting transistor. So this is the reason why we place a shorting transistor. So to put everything in a nutshell, the shorting transistor is used to provide a DC leakage path from either node L3 or node L4 to ground. Without the leakage path, that node would be susceptible to charging by leakage currents, right. So if you don't have that, this node value can become disturbed because of this leakage path. The latch could then actually change the state, which we do not require, right. During evaluation, it has to remain for one input alone. If input go on changing continuously also, it should not change or it should not reflect. So this is achieved by means of this shorting transistor. So thank you students. I hope you would have understood the operation of sense amplifier